Hey guys, we've made it to the end of our ionic bonding unit. And at the end of this unit, we're going to have a little conversation here about the structure and properties of metals. Now, the reason why we're talking about this in the ionic unit is because it's a perfect time to sort of draw a stark contrast between how a crystal lattice structure gives an ionic compound its particular properties and how this structure that we're going to talk about today gives metals a totally different set of properties. So if there's anything that I want you guys to really leave chemistry with, it's this understanding that structure determines function. And the reason why certain substances have certain properties is because of what their arrangement is like on the atomic or the submicroscopic level. So when we think about the ionic compounds that we've been learning about, those are compounds that are formed between a metal and a non-metal, which results in a positive charge and a negative charge on your cation and your anion. And that structure arranges itself in a formation that we call a crystal lattice. And that's a very strong structure, but it's also rigid, like it breaks when a force is applied. It's brittle. Those structures give ionic compounds very high melting and boiling points. It allows these substances to be conductive, but only when they are dissolved in water. So we're going to be thinking about those properties and structure as we look at substances that have a totally different set of properties. Okay, so in order to understand metals, I want you to just think about the metals that you already know, right? Like you're really familiar with what it means to be metallic. Like think about aluminum foil. You've seen aluminum foil, you know how that behaves. Think about copper wires. If any of you guys do any of your own sort of electrical work around the house. So aluminum foil, copper wires, these are substances that are made up of pure metals. And what is holding together a sample of aluminum, or what is holding together a sample of copper? Like why aren't these atoms of these elements just floating off as gases? There must be this force that's holding those samples together. And that force is what we call metallic bonds. Now, these aren't bonds in the sense that we're not talking about a compound here. Like I'm truly talking about pure aluminum and pure copper, or pure zinc, or name any metal. I'm talking about a pure sample of that metal. The force that holds that pure sample together, we call a bond. But it's not a bond in the sense that it's not one atom of one substance bonding to another atom of another substance. When we say metallic bonds, we're just referring to the force that holds together atoms in a sample of a pure metal, like we were talking about up here, aluminum, copper, zinc, or a mixture of metals. And we don't call mixtures of metals compounds. We call them alloys. And we'll talk more about alloys down at the bottom of our notes page here in a minute. So what we're referring to is this force that's holding together these samples. And this is a diagram of what that structure looks like at the atomic level. And we call this structure the sea of electrons. This is the name of the model, just like the crystal lattice was the name of the model for ionic bonding. Now, what's going on here in this sea of electrons? Well, metals have very low electronegativity values. Remember we were talking about, this love for electrons, right? Very low, meaning they don't really care about their electrons very much. They have low electronegativity values and low ionization energies. So what does that mean? It means that they don't really need or want their valence electrons. And so when all you have is a sample of metal atoms, none of those metal atoms particularly care very much about those valence electrons. So the valence electrons are free to roam around that structure. between all of the atoms present. In other words, like let's say that this was an atom of silver. This atom of silver doesn't really care about its one valence electron, so it lets it float around the structure. And sometimes that electron will be attracted to that atom, but sometimes that electron moves and is attracted to another atom of silver. This free-floating electron, these things are called delocalized electrons, meaning they have no set location. They are free to move and attract to any of the particular atoms in this structure. And because the silvers have sort of let go of their valence electrons, they now have a positive charge. So you can see that these cations, these positively charged atoms here, they all stay very orderly, in a very orderly arrangement. Like they're not going to be very close to one another because remember, positive charges will repel. And so these big cations sort of stay very rigidly locked in place. However, these electrons are free to move. And the fact that these electrons are free to move gives a metal very, very different properties than an ionic compound. So what can these free-flowing delocalized electrons, what can they do? Like what sorts of properties do they give metals? So it's all about, the whole key are these delocalized electrons. And just think about metals. What do you know about metals? Metals are shiny or lustrous. The reason why metals are shiny and lustrous is because free-flowing electrons, they reflect light very well. So as these electrons are moving around the structure, if a wavelength of light were to come in, it would bounce back off very well, off of those free-flowing electrons. And so you would, in fact, be able to see a shine to the surface of the metal. What else can metals do? Metals are malleable, meaning they can bend. They are not brittle. And that is because these free-flowing electrons, if we were to apply a force here and try to like squish together this positive cation with this positive cation, like if I were to hit this with a hammer, what are the odds that I can draw a hammer? Yeah, I can't. Ignore. What does the hammer even look like? Nope, that's a disaster. But let's say that there's a force applied. If we apply a force, this positive and this positive would want to repel one another. But the good news is that because these electrons can move, they can sort of swim in between these positive charges and prevent that cation-cation repulsion. So free-flowing electrons prevent cation repulsion. And shattering. So in an ionic compound, I didn't get a chance to show you guys this on the demo the other day because I didn't have any rock salt. But if you take a hammer to some rock salt, maybe you guys have some at home, in an ionic compound, so don't draw this in your notes, but in an ionic compound where there are no free-flowing electrons, if I hit this with a hammer, if I apply a force to this, the negatives are being pushed together and the positives are being pushed together, and there's no free-flowing electrons, right? Like the electrons are assigned to this anion. They cannot move. So what you get is you get a repulsion of charges in an ionic compound. So when there's a force applied to an ionic crystal lattice, you get this repulsion of like charges and it breaks. It's very brittle. So that's the key difference between an ionic compound and a sample of a metal where the electrons are free to move and prevent that repulsion. Okay, and then lastly, metals are conductive even in the solid state. So in an ionic compound, remember, in order to get this substance to conduct electricity, we had to dissolve it in water. We had to get these charges free flowing in that water sample. Here, the charges are already free flowing. The electrons are already freely moving throughout this structure. So if I try to pass a stream of more electrons, which is what electricity is a flow of electrons, they just jump right into the electron sea and pass right through the other side. So they can do this in the solid state versus ionic compounds, which needed to be dissolved in water in order to be conductive. So free flowing electrons carry an electric current or charge. So, structure determines function. Crystal lattice of the ionic compounds, very different sorts of properties than metals, and that's because our ionic compounds have a crystal lattice structure where there are no free-flowing electrons. The electrons were transferred to the anion, versus metals, which have this sea of electron structure, which is very different, and these free-flowing electrons give metals very different properties. But let's say we wanted to, maybe improve the strength of a metal sample that we have, or we wanted to adjust its melting point. Let's say that the metal that we're working with doesn't have all of the properties that we want. We can get different properties of metals by mixing them together. And that's what an alloy is. An alloy is a mixture of two or more metals. For example, brass is a mixture of copper. Is it copper and zinc? I have to go back and look it up. I forget. Yeah, copper and zinc. And bronze is a different copper alloy. Bronze is a mixture of copper and tin. SN. Copper and tin. So these are two different alloys of copper. You can also actually make an alloy by taking a metal and mixing it with a nonmetal. But instead of bonding it to a nonmetal, which would make it ionic, you just mix the substances together. And steel is a common alloy of iron and the nonmetal carbon. So it doesn't have to be metals. You can actually have a mixture of metals and nonmetals, or metal and nonmetal mixture. The key is that you don't have that transfer of electrons. So you would not want to be forming a compound between iron and carbon, but simply mixing them together. And that would just depend on the conditions in which these substances were put together. Okay, now the reason why we would have mixtures of two or more metals is to get a slight change in properties. Get a change in, melting point, strength, shine, malleability. Oh, I'm running out of room here. Maybe you're doing it just for cost purposes. You want to mix together a more expensive metal with a cheaper metal. Lots of reasons to make different alloys. I feel like there was something else I wanted to talk about alloys, and now I can't remember quite at all what it was. Should I pause my recording so you guys don't have to listen to me sit here and wonder about it? Yeah, maybe I'll do that. Okay. I remember what it was that I wanted to do. I wanted to draw this sea of electrons model, but for an alloy, just so that you could see that the sea of electrons was the same. Okay, so let's say I'm making an alloy with copper and zinc. Like, what would that look like at the atomic level? So what I would have is if I had pure copper, let's say I had pure copper. Here's what my sea of electrons would look like. So here are my copper cations, and they all have this positive 2+ charge, because they have let go their 2 valence electrons. Well, those of you that that learned about these exceptions to the number of valence electrons, copper actually only has 1 valence electron. So how on earth could it get this 2+ charge? Remember, they can also donate their d block electrons as well. So if this is a copper 2+ sample, we would have 2 electrons being donated to the electron C. So for every copper atom, there are just 2 free-floating electrons moving all throughout this structure. And that's what my sea of electrons would look like. And they could just move around, and this would be shiny and malleable and conductive. But what if this was an alloy brass? Like, what if this had some zinc inside of its structure? If that was the case, we would just essentially change out a few of these copper atoms for zinc atoms. And it could be in any number of, different proportions. Like there's all sorts of different percentages in these alloys. But if this was zinc with a 2+, and zinc with a 2+, and zinc with a 2+, I still have this very orderly arrangement of cations, because they're going to repel each other. They're not going to want to be right next to one another. And they're very large, versus these small electrons that can flow around. We still have this orderly arrangement of cations, but now, because some of these are zinc and some of these are copper, this is now a sea of electrons model representing brass. Okay, and so that's all I wanted to talk about, you guys. Good job today.